this video where we're going to discuss rates of change. One of the main applications of calculus is determining how one variable changes in relation to another. We're going to look at two types of change, the average rate of change and instantaneous rate of change. So for average rate of change, of a function, we'll call it f of x, with respect to x, for a function f as x changes from a to b, we have this expression f of b minus f of a over b minus a, which if you look at this formula closely, you can see that it's related to the slope formula. For a line that would pass through the point a, f of a, and b, f of b. Here's an example, which you can pause the video and read the example on your own. The United States population is becoming more diverse based on the US Census population projections for 2016 to 2060. The projected Hispanic population in millions can be modeled by the exponential function h of t equals 46.82 times 1.0151 to the t power, where t is the number of years since 2000 and t is between 16 and 60. Use h to estimate the average rate of change in the Hispanic population from 2020 to 2030. So we're looking at this one interval and we're trying to determine the slope basically of the line that would pass through those 2 points on that curve. So the way we're going to do that is we're going to take our function and we're going to find h of 30 minus h of 20 over 30 minus 20. Okay, and that's on the interval from t equals 20, right? So that's 20 years after 2000 to t equals 30, which is in 2030 is 30 years after 2000. So the average rate of change would just be h of 30 minus h of 20 over 30 minus 20. So now I want to figure out what h of 30 and h of 20 is. So I'm going to go in here to my calculator. I'm going to clear out anything that's in there already. And I'm going to type in my function, which is 46.82, and then times 1.0151. And then it's to the t power. We don't have t on here, but we can use the caret symbol for our exponent and then just use x. And then hit enter. And then I want to go to my second window for table set and make sure that your independent variable x says ask. And then we'll go to the table, so second graph, and we're going to delete each of these. And I'm just going to plug in the 30 and the 20. So first we're finding h of 30, so that would give me 73.40. And then if I find h of 20, that's going to give me 63.18. And actually, if you were to hover over that, right, it's 63.184. So let's carry it to like 3 decimal places to be more exact. So I'm just going to take those and transcribe them over. So here we would have broken down, we would have done 46.82 times 1.0151 to the 30th minus 46.82 times 1.0151 to the 20th, all over 30 minus 20, which is 10. And remember, we got 73.400 minus 63.184 divided by 10. And if I subtract the numerator, I would get 10.216 over 10, which we know is just moving the decimal back one place to the left. So that would just be 1.022. So what that means is, based on this model, the estimated Hispanic population would increase on average at a rate of 1.022 million people per year between 2020 to 2030. And it's important to say based on this model because models change, right? So based on this model, the estimated Hispanic population will increase on average. We know it's not going to be exactly 1,022,000 people per year, but on average it will be, okay? And that's between 2020 and 2030. You can pause the video and then try the next problem on your own and unpause when you're ready to move on. Let's talk about instantaneous rate of change. So, you probably see the word instant in that phrase there. So here we're looking at more closer or smaller intervals where we're trying to find the slope. Okay, so it's going to be over a smaller interval. In the last problem we did, we looked at an interval of over 10 years. So if we're looking at instantaneous rates of change, we would want to look at even smaller and smaller intervals, which really, if you think about it, is similar to looking for limits, right? Which is something we discussed in previous videos. So suppose a car is stopped at a traffic light. When the light turns green, the car begins to move along a straight road. Assume that the distance traveled by the car is given by the function s of t equals 3t squared, for 0 is less than or equal to t, which is less than or equal to 15, where t is the time in seconds and s of t is the distance in feet. We have already seen how to find the average speed of any car over any time interval. That was with average rates of change. We now turn to a different problem, that of determining the exact speed of the car at a particular instant, say t equals 10, right? So 10 seconds. In other words, the exact speed at t equals 10 is the limit of the average speeds over shorter and shorter intervals near t equals 10. So here's just a little brief snapshot of what that would look like if we were to look at smaller intervals. So maybe from 10 seconds to 10.1 seconds, and then 10 seconds to 10.01, and 10 to 10.001. So think of it as like the tables we created where we're getting closer and closer to 10 seconds. And you can see that the values are approaching 60 feet, right? So we've got t, which is time, and that's in seconds, and we have s, which is the speed, and the distance is in feet. So these values here represent feet per second. So in the interval of 10 to 10.1 seconds, the average speed of the car was 60.3 feet per second. And in the next interval, it's 60.03 feet per second, and then 60.003. So as you get closer and closer to 10, you would get, the limit would approach 60. Okay, so we can confirm this, though, algebraically, which I'll show you here in a second. So the results suggest here that the exact speed at t equals 10 seconds is 60 feet per second. Okay, and we can confirm this by computing the average speed from t equals 10 to t equals 10 plus some value, we'll call it h, right? So here h is 0.1, 10 plus 0.1. Here h is 0.01, here h is 0.001, okay, and so on. So that's how we create our smaller intervals, right? H is just a small non-zero number that represents a small change in time. So here it's, 0.1 seconds, right? 10 plus 0.1. In the next interval, we looked at 10 plus 0.01 seconds, and then 10 plus 0.001 seconds, and so on. And you would see that the limit would approach 60. So if we apply our formula that we looked at for average speed, right, we took our y values, and in this case our function's s, and we did y2 minus y1, and then of course over x2 minus x1. Okay, well, I know that my function is s of t equals 3t squared. So this is just telling me I'm going to replace 10 plus h in for t. So I'm going to have 3 times 10 plus h squared minus whatever s of 10 is. And then I'm going to divide by, these 10s cancel, and you're left with h. Okay, and then I'm going to expand 10 plus h squared. And of course, that would just be 10 plus h times 10 plus h, which would just give me 100 plus 20h plus h squared. And then 10 squared is 100 times 3 is 300 all over h. And then I would distribute through, and I would get 300 plus 60h plus 3h squared minus 300 over h. And we can see that the 300s are going to cancel. So I'm left with 60h plus 3h squared over h. And of course, we can factor an h out. And the h's cancel. And then I'm just left with 60 plus 3h. So now remember that we're looking at the limit, right, as h approaches 0 of s of 10 plus h minus s of 10 over h, which is the same thing as the limit as h approaches 0 of 60 plus 3h. And if we plug in 0, that just goes away and we're left with 60 feet per second. So h approaches 0 represents the time interval getting shorter and shorter, right? H is approaching 0. We can see in our table, h is approaching 0 as I go from top to bottom. So the exact speed, in other words, at 10 seconds is the limit as h approaches 0 of the average speed over the interval from 10 to 10 plus, whatever that value is, h. So instantaneous rate of change for a function f when x equals a is the limit as h approaches 0 of f of a plus h, some value, minus f of a over h. Okay, this is also known as the difference quotient. So if you see that term, it's also referring to the instantaneous rate of change. And of course, this is provided that the limit exists. But make sure you take note of the following. So the quotient rule for limits that we talked about in 3.1 can't be used to calculate the instantaneous rate of change, right? So this looks like the quotient rule. Since the limit as h approaches 0 of h is actually 0. So the numerator also approaches 0 as h approaches 0. You would end up with indeterminate form. So that's why we can't use the quotient formula. So to find this limit, you want to first try to simplify the expression by factoring an h from the numerator, which is what we did right here. So the h's would disappear. Otherwise, again, you'd get 0 in the denominator and the numerator, which would be a problem because it would be indeterminate. And then please also note that f of x plus h is not the same thing here as f of x plus f of h. When we talk about velocity, we're referring to how fast something is moving and we're also talking about the direction it's moving in. And when we say direction, we're referring to positive or negative. Velocity is the same as instantaneous rate of change. Okay, if you look at the last problem, we looked at the speed of the car, which would be 60 feet per second. So, that is how fast it's moving. And also, since it's positive, I know it's moving in the positive direction. So it's increasing. So its velocity is the same thing as instantaneous rate of change of a function that gives position in terms of time. The reason it's not speed is because speed is not negative, right? So speed is just how fast something is traveling. Okay, you can pause the video and try finding the average velocity and also, and that would be from 2 seconds to 4 seconds. And then also find the instantaneous rate or instantaneous velocity, instantaneous rate of change, same thing, right, at 4 seconds. A company is making alumni t-shirts for homecoming weekend where they expect to sell at most 10 cases of shirts. The total cost for manufacturing X cases of the t-shirts, including the initial setup cost, will be C of X equals 50 plus 75X minus X squared, where X is between 0 and 10. We want to find the average change per case and the total cost if the number of cases manufactured changes from 1 to 5 cases. So we're looking for average rate of change here, right? Which we know we're just going to do C of 5 minus C of 1 over 5 minus 1. So we're just plugging in the 5 into X, and you would get 400, and then we're plugging in 1 for X, and when you do that, you get 124 over 4, and you end up with 69. So What that represents is the total cost, and again, this is on average, increases, since it's positive, by $69 for each additional case when the production increased from 1 to 5 cases. Okay, remember, we're dealing with slope, right? Slope is a change in y over a change in x. So the price is your y, right? The cost. X is the number of cases. So if you picture the 69 over 1, you've got the cost up here and cases there. So for every additional case produced, it's going to cost, the cost will increase by about $69 on average. The next question says, find the additional costs when production is increased from 1 to 2 cases. So this time we're just finding C of 2 minus C of 1. And we're going to end up with 196 minus 124, and 2 minus 1 is 1, right? So I don't have to worry about dividing by 2 minus 1. It's just 72. And again, it's just the additional cost to produce the second case is $72. Find the instantaneous rate of change of costs with respect to the number of cases produced when just one case is produced. All right, so now we're looking for instantaneous rate of change, which we know is just the limit as h approaches 0 of C of 1 plus h minus C of 1 over h. Okay, the 1, again, representing the one case that's produced. That's your x plus your h. Okay, so now we're going to break this down. I'm going to need some room for this. And if you had issues with solving this problem here, the check your understanding number 2, part B, this part that I'm doing with you will help you go back to B and determine if you did it correctly. So what I'm doing is I'm taking my function, which was this function right here, and I'm plugging in 1 plus h for the x's, and then I'm just plugging in 1 for the x's. So when I do that, I get the following. I get 50 plus 75 times x, which is just 1 plus h, minus x squared, so 1 plus h squared. And then I'm going to plug in actual 1. So I would get 50 plus 75 times 1 minus 1 squared. And in the denominator, we're just going to divide by h. Okay, now you're going to want to go through and you're going to want to expand. So you would want to distribute the 75, and then you would want to FOIL this out, and then simplify that also. So you would get the limit, and then it would be 50 plus 75 plus 75h minus, when you FOIL out 1 plus h squared, you end up with negative 1 minus 2h minus h squared. And then I'm going to just simplify this real quick. That would be 50 plus 75. That's 125 minus 1. So that's just going to boil down to negative 124. And then all over h. So simplifying further, you get the limit. And then I'm going to combine some terms. So let's see. When I combine here, 50 plus 75, that's 125 minus 1 is 124, and then minus a 124. So those terms are all just going to go away. And 75h minus 2h, that gives me 73h, and then minus h squared over h. And you can factor out an h, so you're left with h times the quantity, 73 minus h over h, and the h's cancel out, which is great, because when you go to evaluate h equals 0, you don't want it to be indeterminate, so then you would end up with the limit as h approaches 0 of 73 minus h. If you plug in that 0 there, you get 73. So that's the instantaneous rate of change. And it just means when one case is manufactured, the cost would be increasing at a rate of about $73 per case. Again, on average, right? So let's write that down, which will help you interpret, because that's important. You find an answer, but then what is that answer? Like, what does it represent? Okay, so when one case is manufactured, the cost is increasing at a rate of $73 per case. If you'll recall, economists sometimes define marginal cost as the cost of producing one additional item. Okay, so basically that's what we just found, right? Going forward, we'll assume the marginal cost is the instantaneous rate of change of the cost function, and it can be interpreted as the approximate cost of producing one additional item. You can pause the video, and now what I'd like you to do is for that cost function in the previous example, find the marginal cost when the 5 cases are made. We just found the marginal cost when 1 case was made. This will give you good practice. In this last problem here, we have a problem about a dog named Lady, which says one day, Lady, who's a friendly Labrador Retriever, escaped from the yard and ran across the street to see a neighbor who was 50 feet away. An estimate of the distance Lady ran as a function of time is given by the following table. So here you have the distance traveled in seconds, and then you've got the speed in feet. We want to find the average velocity during Lady's 4-second trip, and then estimate Lady's velocity at 2 seconds. Okay, so we need to know 2 things here, right? We need to know the distance traveled for 4 seconds, and we can see that that's 50. And we need to know the speed at that time, which was 4 seconds. So if I want to find the average velocity, that's just going to be the distance divided by the speed. And that's going to give me 50 divided by 4, which is 12.5, and it's feet per second. So that was Lady's average velocity. She was running 12.5 feet per second during her 4-second trip. Okay. So now what would Lady's velocity be at 2 seconds? We could estimate her velocity by taking short time intervals from 2 to 3 seconds, and then maybe like 1 to 2 seconds, and then average the 2 together. So maybe for the 2 to 3 seconds, we would take, so 2 to 3, time equals 2 to 3. We could just find f of 3 minus f of 2. So that would be 42 minus 25 over 3 minus 2. So that would just give us, 17 feet per second. And then maybe I want to do 1 to 2. So if that's the case, I've got 25 minus 10. Over 2 minus 1. So that would be 15 feet per second. And then maybe take the average of those 2 smaller intervals. And 17 plus 25 over 2 is how I would find the average. that would just be 42 divided by 2, which is, let's see, or sorry, yep, 42 divided by 2, which is 21 feet per second. It would be impossible to, that should actually be 17 plus 15, not 25. So that would mean it's going to be 16 feet per second, which makes more sense, right? I mean, if she's traveling 17 feet per second from 2 to 3 seconds, and then 15 feet per second from 1 to 2, the average would be about 16 feet per second. So that would be her velocity at 2 seconds, approximately. Even though it's impossible to calculate the exact velocity because there's other variables involved, like lady's position at the times that are close to 2 seconds, etc. So, but that's it for this section. In the next section, we're going to be looking at definition of the derivative, and it's an important one. If you have any questions, please reach out.